today's mechanical engineering seminar. This is my pleasure to introduce our seminar speaker for today, Dr. Michael Filler. Material science and engineering. His research program lies at the intersection of chemical engineering and material science. He focuses on the synthesis, understanding, and deployment of nanoscale materials for applications in electronics, photonics, and energy conversion. He's been recognized as a recipient of the NSF Career Award, as well as the Georgia Tech Sigma Chi Young Faculty Award and the Camille and Henry Dreyfus Foundation Environmental Chemistry Mentor. With that, I'd like to welcome Michael to the stage.
Great. Thank you, Kira. Thank you all for coming here and online. Can you maybe minimize the video here? I didn't think.
The camera won't be able to see you if you're over here.
Oh,
Just
where should I stand? I'll stand more here.
Yeah.
Okay, I'll stand more here. Okay. Well, I'm going to tell you a story that I embarked upon a couple years ago now. One of the points in that story was when I met your very own Kira Barton. It's a story of how to think about making things, and specifically making electronics. The work that I'm going to show you has been largely funded by the National Science Foundation and more recently DARPA. Now that was working before. I think. Let's try that. Yes. Okay. So, of course, I have the pleasure of traveling and visiting places like University of Michigan, and my students are the ones in the laboratory doing the hard work. And the work I will show you today is largely by Amy, Maritza, and Amar. And then this is some of the team members who have contributed at the PI level. So myself and then my close colleague Eric Vogel, Kira, Eric, and I started collaborating a couple years ago. And then Victor and Sven, I think I'll unfortunately leave off the work by Jerry. But these are close collaborators who, because this is such a interdisciplinary project and vision, it needs more than one technical domain. So here's what I'm going to tell you. They say tell people something, then tell them what you told them. And so this is what I'm about to tell you. I'm going to tell you that the future of electronics, there are use cases that necessitate extreme scalability, on-demand manufacturing, and mass customizability. Okay. I'm going to tell you that the principles of today's IC manufacturing are really antithetical to these needs. Okay. It is unlikely that we will achieve number one without changes to number two. And we're developing this thing called nano-modular processing, which we think is a really intriguing way to move forward. For those of you who don't work on nanomaterials or the specifics I'm going to tell you about, what I want you to keep in mind is that we think nano-modular processing is very general. It's general to electronic circuit architecture, device operating principle, material, you name it. It's a process kind of way of thinking. And so you can apply different materials and architectures to do nanomodular processing. I will show you one embodiment, the one we are specifically working on, but we think there are many ways to do this. So this is the design space of today's electronics. You all know and love this. Maybe you haven't been to a data center, but you more or less know that this is the world we live in today. And this world has been enabled by this curve. This is cost per transistor as a function of time. Okay? This is what we also refer to as Moore's law. Okay? And this has decreased, as you can see, 7 orders of magnitude on the order of 50 years. It is one of the most impressive human achievements of all time. And today, a modern transistor is on the order of 5 times 10 to the minus $8. It's remarkable. And I'm here to tell you, maybe that's not the whole story. Okay. So if we look at the numbers, we look at other metrics besides just the cost of transistors, or that's kind of the main thing, I guess. But if we look at other metrics, things we should maybe wonder about. The first one, how many different kinds of devices can be incorporated on a traditional integrated circuit? It's usually just one. Sometimes if you work really hard, it's maybe 2. How long does it take to make an integrated circuit? Months for most circuits. You know this from all the supply chain disruptions, the fact that you can't buy a car because there's circuit shortages, chip shortages across the world. Okay, it's too long to make a circuit. How much does it cost to make a unique circuit? Inexpensive one is $10,000 per circuit, and a high-end one, like in a mobile phone, is millions of dollars per unique circuit. A fab is hundreds of millions to tens of billions of dollars. There's a small group of people who have the resources to build a modern fab. The footprint is football field size, and many football field sizes in many cases. And then the cost per device. But wait a minute, I just told you that was one of the best things about electronics, how cheap a transistor is. Turns out though, if you take this data and you replot it, as a chemical engineer would like to see it, okay, you plot it cost per mole now. That's 10 to the 23 transistors, okay, instead of cost per individual transistor. It still decreases by 7 orders of magnitude. But when you compare the present day cost to that of highly functional molecules produced at a massive scale, like the pharmaceutical Lipitor, there are 10 orders or more magnitude difference in cost. There is a gaping hole between what can be done with the way we make circuitry today on silicon wafers and what the chemicals industry has been able to do in its manufacturing paradigm. Now, I'm not saying we're going to make transistors as cheap as gasoline. That's highly unlikely. But I'm saying that there is a hole between Lipitor and transistors you can drive a truck through. Okay. There are other problems with the industry today. I mentioned COVID a second ago. That is one, supply chain disruptions. This on the left is increasing cost for developing the next chip generation. It's going up at 50% a year. Very hard to keep that up. On the right is the consolidation of manufacturing. We have gone from a nice ecosystem 20 or 30 and longer ago years to like 3 players that can make chips. That's one of the reasons we're having supply chain shortages. We have consolidated and centralized manufacturing, and when one has a disruption, the whole world has a disruption. Don't get me started on the carbon footprint, and we can talk later about the geopolitical considerations, but there's one a company in particular, a TSMC, that is at the center of geopolitical friction right now, let's say. Okay, these are all problems. For all the good, all the impressiveness of modern IC manufacturing, these are challenges that if we want to see the future that we hope to see, we need to think about changing. So what metrics should we go for? Well, in the future, I'd like to see any number of devices can be really mix and matched. Let's just say 10 is a reasonable number, okay? I want to be able to make circuitry on the order of minutes, maybe a day for a complicated circuit. Each circuit should cost cents to dollars. The cost per fab should be on the order of 1,000 to tens of thousands of dollars, maybe 100,000 for a fancy fab. Think about 3D printing. Like there's a range of 3D printer technologies, from something you can buy on Amazon to something that you'd buy and put in a factory somewhere. Something that can fit on this desktop, something you can put in your car, you can fly on an airplane. And then finally, let's get devices even cheaper. I think we can easily do 4 or 5 orders of magnitude. And then we can all be like that. And by the way, I can watch that baby all day long. Okay, that is the world's awesomest baby in my opinion. Okay, so if we can do that on the right-hand side, if we can do that, what will the future IC technologies look like? Well, first of all, they'll be natively heterogeneous. Okay, these will be where we have a variety of devices we can mix and match to make distributed sensor nodes that all do power harvesting and computation and all sorts of stuff very naturally. I think things will be on demand and distributed. Rapid, mass customizable circuitry, a lot like 3D printing. Things can also be dispersible, disposable. I'm going to show you an example of that. Basically where you can disperse and you can throw electronics into the air. I'm not sure you would do that, but there are ways that you would use electronic circuitry that could be dispersed. And that also circuitry that could be reconfigurable, that you can change the arrangement and identity of the devices dependent on the workload. I'm going to talk about the middle two for a quick second to give you a feel for what I'm talking about. So that's the conventional fab on the left, $10 billion. That's one part of a $10 billion fab. And that's what we're going for on the right, is circuitry out of a printer in a dorm room. What would you do with that? Well, the dorm room is, meant to be, provocative. But if you think about a doctor's office, tremendous advances in bioelectronics in the recent decade or two. People are injecting electronics into mice. People have startups that are working on ingestible pills, things that monitor your insides or eject drugs given your disease state and your anatomy, and that they're programmed for you. Right? Tremendous opportunities going forward. I'll tell you right now, I don't really want these to be software programmed. I want them to be hardwired, and I want the doctor to know my anatomy and basically print that circuit so no one can hack the pill I'm about to take. Okay. And we have a global population of 10 to the 10. So you can imagine every person needing a different pill designed for a particular situation. Mass customization. I think there's a lot of opportunity to bring cryptography into the real world, into the physical objects all around us, starting with high value things like avionics and pharmaceuticals, where you can basically have individual circuits that verify the identity of the manufacturer, the time it was manufactured, the supply chain, et cetera. But again, you need mass customization. I mean, there's many, many more parts than there are people on the planet. Got to bring the cost down tremendously if we're talking about these kinds of applications. So that's kind of on-demand, mass customized, and I think there'll be lots of other things that other people smarter than me will figure out to do with a printer technology like this, a lot like what people did with 3D printing. Okay, it just kind of blossomed once the technology started to become available. I've given a seminar in mechanical engineering. It's really a pleasure to do that. You know more about this than I do. Okay, this is a turbofan engine. I'm not even going to tell you how it works. I could try, but basically, right, we compress air and we ignite it here with fuel, and then we use the hot gases that are generated for thrust. This is extremely hot right here, and my colleagues at Georgia Tech will tell me that the details of this are difficult to measure directly. Yet those details really matter in terms of efficiency, thrust, lifetime. A lot of factors that affect an engine. DARPA had a call, it's about 5 years ago now, looking for new semiconductor materials that operated at high temperature. So silicon operates up to about 200 before it falls apart. And they were looking for some fancier wide bandgap materials. They wanted those sensors and electronics to sit at 800 degrees C and operate. And they were thinking about applications like this. So that's kind of the, hold your hand in a candle solution, that it needs to be robust for at steady state for the entire lifetime, right? Or for a long enough period of time. We all know holding your hand in the flame of a candle is hurts. So we also know that when you pass your hand through a candle flame, you can do that and not burn your hand, right? So you could imagine with dispersible electronics that you intentionally fire wireless sensor nodes through an engine. And what they do is they detect temperature locally, and they wirelessly send back that information to radios that are sitting on the outside of the engine. Okay. You need high enough performance electronics to do this, to get to the frequencies that allow you to have decent information transfer from a sensor node to something sitting outside the engine. But this is what I'm talking about. Driving down the cost of electronics enough, keeping the performance high so you can do a lot of the things we take for granted with silicon, but do it at a scale where you just shoot them at the millisecond. And by the way, I should say that you're going to consume these like one every millisecond, right? So really cheap and consumable electronics. Lots of challenges here, by the way. I mean, this is not meant to explain exactly how you do this, but these kinds of opportunities I think are real if we can change how we build electronics. We've tried this. We've tried to make more scalable, lower cost electronics for 2 or 3 decades now. This is a plot of performance versus manufacturing scale. So where you want to be is actually up here. High performance, high speed, low voltage devices, low cost, very high throughput. In general, what we've done with a whole variety of materials over the last 2 decades is been stuck on a line that looks like this. We trade off one for the other. Here's silicon CMOS, what you have in your pocket right now. We can get better and we can get worse in terms of performance. We can get a little bit better in terms of manufacturing scale by going to some polymers or maybe some nanocrystals. But we're definitely not here, and down here we lose performance. So how do we get off this trajectory? And this is my contention. This is not a materials problem primarily. This is a problem about how we construct circuitry. It's a process problem. So we have to go back to the process that is the foundation of the entire electronics industry, and that is the planar process. Invented in the 1950s by really the traitorous 8 who left Shockley's company and started Fairchild Semiconductor. Okay. 2 key people were Jean Erny and Bob Noyce. Bob Noyce going on to found Intel after Fairchild. Okay. The left is really the starting point of the planar process. And what Erny realized is that if you embed doped regions into a wafer, you build the device in the wafer, you can make a much better device than building it on top of the wafer. It's called the planar process, but now that the device is basically embedded, the top surface of the wafer is still planar. Okay, and this made much better devices than anything that had come before this innovation. At the same time, or shortly thereafter, I'm pretty sure Bob Noyce realized that if the top surface of my wafer remains flat, it's a lot easier to interconnect the devices to each other to build a circuit. That's where the technology of the 1950s, not necessarily 3D printing or something like that, but in the 50s, those were the technologies they had at hand. They did this, they built the first integrated circuit. All existing IC manufacturing schemes assume this. Much of the work that people have done on polymers unknowingly assumes this. It's almost the water we swim in. We don't realize how wedded to it we are. And there are problems with it. Okay, this is a very, I tell my students, if you have to say at the start of a slide, this is a very busy slide, I apologize, I say change the slide, fix the slide. So I'm gonna fix the slide after this presentation. These are a couple principles I want to point out real quick about the planar process, just to kind of get you to understand why it's so limiting. It's monolithic. This is often pitched as a positive, and in many ways it is, this idea that you are physically embedding devices in a substrate or attaching them to a substrate. But it sets a very high bar. Because things are inside the substrate, it becomes very hard to remove them, to replace defective components, which means that every step must have a near 100% yield. I don't know another manufacturing process that demands that level of perfection at too many of the steps, let alone every single step of the process. This leads to the cost of fabs, the long cycle times, because you can't process very quickly or you'll make a mistake. And that leads to very poor materials flexibility. It's why silicon still dominates. Seamlessness. You always start at the beginning. There's no break point in the process. I always have to start with a fresh piece of paper, a silicon wafer, and build the entire circuit. That's why there's a 90-day lead time. Okay, I'm always starting from nothing versus having a stockpile of something I can start with. Also, all steps must be compatible with all others because you're making everything in one location built on top of a circuit, on top of a substrate. They all have to be compatible, which places severe limitations on your ability to build different components. And finally, this requires a company like an Intel or a TSMC to have extensive process know-how. They have to do every single step in the process. When you're building a car, does Ford Motor Company build every single piece of that car? No, they do not. They integrate for the most part. Okay, I know I'm simplifying it, right? But they definitely don't pour the metal, at least today, to do all the doors. And you get my point, okay? But we do in the semiconductor industry. It's planar, okay? If I have to build everything on a surface, I can only build so fast versus building things in a 3D volume. And finally, top down, which means I put down some material, I pattern it, and I remove what I don't want. That has been the driving force behind nanotechnology for 20 years, and I'm going to put it at the bottom of my list in terms of importance. These things combine to give us a process that has changed the world, but has severe limitations for going forward. So what are we doing? Let me get now to nanomodular processing. So nanomodular processing factors device and circuit fabrication into separate steps. So you can imagine a process like this where you build, say, transistors. These are nanomodular devices. Think of them as process intermediates. Okay, there's something you can put in a tank, you can store, you can ship. And then circuit fabrication, where you take inks, basically you take this process intermediate and find a way to build a circuit. We separate these two steps in space and time. Let's talk about the devices for a second. What do they need to be? Well, really, they're self-contained black boxes. Like if I'm a circuit designer, I don't need to know anything about how that device is fabricated, as long as you can tell me when I apply a voltage, what's the current, right? All the features of those nanomodular devices are pre-built, so the device is fully functional when it gets to the circuit manufacturer. If you had a silicon MOSFET, and I'll show you a structure of one of these in a second for those who don't know what field effect transistors look like. You need these things, and that's what you need. So you have to build all those things ahead of time. At the interconnection point, this is where you're a lot more flexible in many ways. They have to be interconnectable in a standardized manner, but the way and the standardization will be dependent on the application. So that doctor's office printing of a circuit is likely going to be very different, a very different platform than the assembly of a circuit to fire circuitry through an engine. Okay. But they'll likely both come from devices that are modular. And this is, I think, really important. So when you break a device fabrication and circuit fabrication in space and time, I think you can dramatically accelerate the pace of innovation in electronics. Because you can create entirely new device and circuit supply chains and ecosystems. A lot of these things can be developed separately. There are people who have spent their lives doing things with electronic devices, never to see them ever incorporated in a circuit because it was too hard. And that is a shame. We spend countless R&D dollars when making new remarkable devices, for example, that never go into circuitry. I would like to change that. Extreme customization, I hope that's fairly obvious. Both in terms of what you can integrate and the diversity of processes you can use to build the different pieces. Enhancing supply chain robustness. Imagine having a tank of transistors that you can deploy to make any circuit you need in that moment. Or if you're a Ford Motor Company, you need some circuits, you just make them. There's some other benefits too. Those are kind of the big ones. I think there's a lot of cool things you can do. So these ICs will have a different look and feel from the circuits we are familiar with today. So this is a plot of integration, like how many devices can I put together in a single circuit versus manufacturing scale. And so this is what's in your mobile phone. 10 billion transistors interconnected into a single circuit. Where will nanomodule processing be? It'll probably be over here. Low cost, high throughput. On an individual circuit, maybe it's 1,000 or it's 10,000 transistors. But the number of applications, when you can do that in a fully customizable manner, I think is tremendous. Why do I think that this is a reasonable thing to try? I don't know. The only thing I have going for me is that the rest of the manufacturing world is largely modular. IC manufacturing is the oddball here, if you look at manufacturing writ large. I mentioned cars already. You might be saying, well, but show me electronics, Mike. I don't believe cars are, that's not electronics. Okay, even though they're full of electronics. Okay, here, this is a circuit board. These are individual modular devices soldered to a circuit board. Again, modular components. Length scales are much bigger than what I'm talking about, but still modular. You might say, well, but your transistors you're talking about are really tiny. I think molecules are modular too. So if anyone knows what the Aldrich catalog is, right, it's just basically a gigantic catalog of molecules you can buy. So every single one of them is a modular entity that chemical engineers and chemists combine in unique ways to make functional things. And they're modular too. To me, the history of manufacturing is about modularity and the benefits that accrue to modular platforms. Okay, that's a long intro. I know it's probably the longest intro you've ever seen in a talk. So hopefully I kind of painted a picture for you of why this is an interesting direction of research to pursue. Now let me show you some science. I'm going to show you two pieces of science. The first one being our work towards device fabrication and the new processes we've had to develop to do that. And the second part is scale up. How do we decrease the cost by orders of magnitude? Okay, so let's talk about devices, and not just any devices. We want them to be silicon level devices. I joke with my students all the time, if we can have late 1990s silicon transistors in a cup, that would be awesome. Like that's what we're going for. So what do you need to make a good transistor? let's say that's going to be our future transistor. For those who haven't seen these before, this is the basic structure. You have a source from which electrons come from. They traverse a channel, which a gate is over, and they go to the drain. So the charge is going to generally go this way. And it only goes that way when you apply a voltage to the gate. So here is that same thing with a voltage applied to this gate, basically turning on the switch, and a potential applied across the source and the drain. You get current to flow. That's the basic idea of a transistor. Well, the first thing you need to make a good transistor is a short channel or gate length. You don't want to let that charge transfer over a long distance, right? The faster it can move from point A to point B, because the distance is short, the faster your device is going to be, the lower voltage it's going to operate at. So that's number one, short transport distance. Number two is a high transport speed. You want it to be moving quickly over that short distance, right? If you can combine the two together, then you generally get a good device. And this is a plot of mobility, basically speed of charge carriers through different materials. And it turns out silicon's really good at this. That's one of the huge benefits. It's not a bad semiconductor. A lot of things people have tried in more recent years are worse than silicon in terms of the speed at which charges transport in the material. So we need to get nanoscale channels and high mobility materials like silicon. There's some stuff you need to also take care of in terms of the interfaces. I will not discuss that any further. And so how are we doing this? So we are growing from the bottom up single crystal silicon nanowires, where when we grow, we create source, channel, and drain. We then apply a process which we call scales, and I'll show you that, where we pattern this source, channel, and drain to create nanoscale masks over the source and drain. And then we use those masks to direct the deposition of a dielectric, and then a metal on top of that dielectric to give you the capacitor structure that makes up the gate of a transistor. And we can remove the resist afterwards. That's the basic idea. There's probably more things we do in the future, but this is kind of the initial piece of work that has to happen. Okay, so let's talk about wire growth. So we use this technique called vapor liquid solid, VLS, to grow single crystalline nanowires from a metal seed particle. And the process is very simple. You deliver a semiconductor containing precursor like silane to this droplet. It reacts and deposits silicon. And when you've deposited enough silicon at a high enough temperature, this is a liquid. It's a liquid droplet. And if you keep adding silicon, then you will precipitate out a single crystal solid nanowire, just like sugar precipitating in water when you add enough sugar. This is the same thing. We add enough silicon to a liquid, and we spit out silicon solid. It's a lot higher temperature than sugar and water, of course. This is on the order of 500 degrees C where this happens. And then the cool thing about this process is we can switch between different dopant precursors, phosphine and diborane, giving us N and P-type doping in that silicon as we grow the structure. And we're pretty good at doing this. So these are single crystal silicon wires with different dopant profiles. And the reason you see this, this diameter modulation is because we've etched the wire selectively in an etchant after the fact. If I showed you the wire immediately after growth, it'd just be kind of a solid structure, even though the dopants were in there. And here we're just resolving it for you so you can see the dopant profile. You can see the nanoscale control that we can achieve in structures like this. And I really think of it as like programming DNA. I mean, we can control, as you can see here, what kind of dopant we want to put in and for how long. Now, if you take a structure like that and you turn it into a more transistor-like structure with a source, a channel, and a drain, and then you apply old-fashioned semiconductor industry type processes to contact it and build a gate, you can show that the wire will behave like a pretty good transistor. This is really pretty good, 300 centimeters squared per volt second mobility. Like that, it's not industry's state of the art, but it's also much better than a lot of quote unquote scalable, highly manufacturable semiconductors. But this is where you can't stop. You can't stop here because now you've taken just one step and applied a whole bunch of old-fashioned techniques to it. You have to keep going, building the whole structure. So here we go. So scales, the patterning step, is analogous but distinct from photolithography. So I hope most people who are listening know what photolithography is and how it works. Bottom line is you take a photosensitive resist, you spin it on a wafer, You expose certain regions with light, and those exposed regions, or the inverse, can be developed away to leave you a pattern. With scales, we leverage the underlying dopant profile. So we grow a wire, we put a polymer on the whole wire, and now it's grown as a brush, actually. So it's not spun coat, we just grow it off the surface, but it's still a resist. And then we have a selective etchant that diffuses through the polymer and attacks the silicon on the nanowire. And a lot like a plant in a pot, if you hold the plant, which is the polymer in this case, and you sweep away the soil in the pot, which is the silicon, the plant comes out really easily. So that's exactly what's happening here, is that the polymer gets released when you etch a little bit of the underlying silicon. And if you keep going and you design this process right, you should have polymer remaining on the regions that don't etch and have it removed entirely from the regions that do etch. This is a bit about how we apply the polymer. I point this out mostly to say that these are largely standardized processes combined in a new way. We didn't invent any new chemistry here. We just used the excellent literature that surface chemists have developed over the last 20 years to attach things to silicon surfaces. Okay, so what do you get? We do a lot of studies on planar wafers because of characterization techniques that only exist for planar things. It's actually really hard to characterize nanoscale objects with a great bit of detail. So we start with planar systems. This is a wafer that we've patterned with heavily doped and lightly doped. And what you're seeing here, these are XPS, photoelectron spectroscopy spectra of PMMA. So these peaks are characteristic of PMMA structure. Basically saying, yes, you have PMMA on the surface for both the doped, heavily doped and lightly doped surfaces. And when we apply our selective etch technique, we remove the large majority of the PMMA from the lightly doped region, and we leave it behind basically untouched on the heavily doped region. This is a little bit of potassium. So this seems to work, as I showed you in PowerPoint on the previous slide. PowerPoint was way easier to draw than to get that science to work. Now let's do it on the nanowire. So here is another one of those test structures. I mean, you can kind of see source channel drain kind of programmed along the length. Just to prove it to you, that's what it would look like if you etched it. Took a fraction of the sample and etched it, but we don't do that initially. So we start with this wire, we grow that polymer, and here I false colored it in green. And then we selectively etch it in KOH. Right, and so if we're really careful, we can get these kinds of nanoscale masks on the surfaces of nanowires. And I'll point out that the spacing between these masks, this channel region, is already deep submicron, 200 nanometers. And that's without trying too hard. Nanowire growth has been shown to get down to tens of nanometers really without trouble in terms of dopant profile control. So we have room to be better. But this is basically quarter micron, late 1990s silicon technology, but just done with an entirely different, mostly bottom-up process. And so Amy is a senior student in the group who has been working on the next step, which is getting the dielectric and the gate to go down selectively. Okay, that's a very busy slide, but this is the heavily doped side, and this is the PMMA basically saying, look, the PMMA is still there, and it is untouched when we try and add hafnia, and it's untouched when we try and add platinum. On the right-hand side, the lightly doped side, right, we removed the PMMA. We no longer see, I guess I'm not having the carbon here, but we have nothing on the surface, basically bare silicon, and then we add hafnia, which is what we want, and then we add platinum, which is what we want. So on the lightly doped region where we're able to remove the PMMA, we can get both hafnia and then platinum to go down. If you look at it in a EDS map, this is the SEM image, and you can see by looking at the hafnia X-rays and the platinum X-rays that the hafnia is where we expect it to be, and so is the platinum right on top of it. This is really light here because the hafnium X-ray overlaps with the silicon X-ray a little bit. Okay, but it basically shows that we can make these capacitors on a wafer using this polymer process plus area selective ALD. And when we measure the capacitive properties of this gate stack, it behaves a lot like what you'd expect to see in a silicon transistor. Okay. Is it the best silicon transistor the world has ever seen? Certainly not. But it definitely looks like a silicon transistor. And we're now working on ways to improve it. And one way has been to remove this hump right here. So these are surface states. These are basically dangling bonds at the interface between the nanowire and the oxide. And it turns out with a forming gas anneal, which is a very straightforward process in the industry, you can get rid of a lot of these surface states. You can see the blue lines kind of go quickly down. And so we've dropped surface states from this level 4x or so to this level. And we think there's more room to grow. In fact, we need to be better because this would not be low enough to get where we want to go. But we already made some nice progress. So it looks like a silicon transistor. It talks like a silicon transistor. It still could be better, and we're working on that. I guess that's the planar one. So this is kind of where we are. This is our state of the art right now on the nanowires. So on wafers, it works pretty well. On nanowires, it's trickier. So these are two different nanowire types. And here we've shown that we can put zirconia, in this case, another dielectric, not hafnia, but zirconia, down in the regions where we had lightly doped P, not heavily doped N. And we can change the dimensions of these regions, and we change the dimension of the zirconia that's wrapped around them. Is the zirconia perfect on the nanowire? Certainly not. It needs to have a better morphology. It needs to have cleaner, more abrupt edges. But this is a first demonstration that on a nanowire with a bottom-up patterning process, you can put down a dielectric where you aimed to put it down. And that's the state of the art in terms of wire growth and device synthesis. And I hope to come back soon and show you that these actually work. I want to say that the next step is a really important one too. Once we have devices, we have to find new ways to interconnect them. And that's where our collaboration with Kira's group is so fantastic, because they're experts in E-jet printing. Is a wonderful, highly resolved, small footprint technique to print metals between the different devices. And I'll just show you a tiny, tiny bit about this. It's desktop size. I was just in the lab looking at it with my own two eyes for the first time, which was really great. And they've already been able to take silver metal lines and get them below 1 micron, which is a really great step forward for the team. And then this shows you a little bit about what they look like when they the particles that are the metal wrap around the nanowire that they're printed on top of. So early stages still, but this is where we're going with Dr. Barton's group. Okay. So that's all about device synthesis. And I want to tell you one last little story about how you make a truckload of devices. Okay, to drive the cost down orders of magnitude, you need to be manufacturing truckloads of devices. For the applications I was talking about, you need to be making truckloads of devices. How do you do that? So a lot of wires are grown on flat surfaces like this. This is older data from my group. There's no doping in this. These are homogeneous wires. It's actually very easy to do this relative to what we're trying to do now. A lot of people do roll to roll. They say, well, just put it roll to roll, be really fast, and you'll solve the problem. I'm here to tell you that there's a reason chemicals are not made on surfaces. There's a reason when you cook for a big party at your house before COVID and hopefully after COVID, you use a gigantic pot and a stove, not a frying pan. Okay, because the throughput of that gigantic pot is a lot bigger than the throughput of a frying pan. And you can only make your frying pan so big. Okay, sounds really silly to say that. But fundamentally, the geometry of where you process matters. Okay, so we are working at finding a way to go from 2D processing to 3D processing, or as close to 3D processing as we can to get that productivity enhancement. And we developed a process we call the Geode process after geodes. Right? Geodes are rock formations where you have crystallites that grow on the interior of some kind of rock. And we're doing that, but our geodes are 30 to 50 microns in diameter. Okay. And they are porous walled. And we line the interior with the little seed particles that drive nanowire growth that I just showed you a bunch of pictures of before. And having this porous wall is really important because it allows gas that we use to grow the nanowires to transport from the outside to the inside, to grow nanowire crystals inside our micro geodes. Okay. I say up here, you can barely see it. It's 2.5D processing. So it's not quite 3D, but it's still on a surface. But it's a very high surface area, right? It's important to keep in mind. This is what the chemicals industry does when they make catalysts for chemical processing. They do a high surface area substrate. You'll make a powder. You'll load it into nothing that looks like a traditional CVD reactor. You'll process it. You'll take out now micro geodes that used to be microcapsules. There'll be nanowires inside like this, and you can either use them like this for certain applications, or for electronics, you can harvest them. I think you can make devices in here without a ton of difficulty. And just to give you a sense for the scale that comes from an approach like this, in one kind of average industry-sized 1 meter cube reactor, you can produce as many devices in about a day as the entire semiconductor industry produces in a year. Just to give you a sense for the scalability that just comes from increasing the surface area of the substrate you're using. How do we make this substrate? It has to be scalable also. And so we use something called emulsion templating. So really simple, you've all shaken vinaigrette before, right? You have oil and water in vinaigrette and you get little droplets. That's an emulsion. We do the same thing, but far more controlled. We take water droplets in a continuous oil phase to start. And the little metallic seed particles are capped with a molecule that makes them hydrophilic, so they go into the water. And the silica particles that will eventually make up the shell of the capsule are a bit hydrophobic, so they go into the oil. Then you wrap that oil phase in another water continuous phase. That's called the second emulsion. And you can see what's starting to happen, right? The metal seed particles remain in the inner water phase. And now you're starting to coalesce these silica particles into something that looks like a shell of a capsule. If you're smart about the oil you choose something that's soluble in water so that the oil leaves and goes into the outer water continuous phase. And when that happens, you get capsules that look like this in water with oil kind of dissolved at low concentration. If you go and dry this, you get powders that look like this. In the SEM, these are what those capsules look like. And you can break them open and look at the interior surface, and you can see the metal seed particles. And the exterior surface has very few of the metal seed particles. They're largely on the inside. And so we filled a dump truck with these. That is a very small dump truck, but we have still filled a dump truck. And if you grow these in a CVD reactor and you grow nanowires, that you get spaghetti-looking things like this. So very high density growth. I show this Raman spectrum, which is basically saying these are silicon wires, because this kind of measurement with a standard Raman spectrometer is not easy to do with usual wire growth techniques. You don't have enough material. Just the sheer fact that we can grow and in a single capsule measure the Raman spectrum is a really important thing to give people an ability to analyze what they have without resorting to very expensive techniques like TEM and other things. So I think it's a really valuable thing to have the ability to do. We could also program the structure. So it's not enough to just grow a bunch of wires. You have to grow devices, right? So I showed you before outside of capsules that we could create these very controlled profiles. This is not silicon and doping. This is silicon and germanium. And we've intentionally encoded these germanium segments in the silicon germanium nanowires. And then if you look at the TEM, when we do harvest some wires, you can see very clearly the modulation between silicon and germanium that we can get inside of the capsules. And we can go all the way down to 75 nanometers. So we have very good nanoscale control, even inside this capsule. The transport of precursors is very good through the wall of the capsule. And that's kind of where we are. So we worked on this for a couple of years, and obviously we've made some nice progress. We have plenty more things to do. So I hope I've convinced you at some level that there are exciting use cases of electronics that are unlikely to be touched by the way we make electronics today. I really think the way we build electronics, it's not going anywhere. It's going to be here for a long time to come, but it is not the only way to build electronics, and we should be thinking about these alternative methods. We're pursuing this idea of nano-modular processing. I've shown you one very specific embodiment, silicon devices And we think it's agnostic really to what the device is. It could be many different things, just like there's many different parts in a car, just like there's many different components you can integrate on a circuit board. If you have an interest in these kinds of concepts that surround process, I encourage you to read this article that I co-wrote with a colleague of mine in the department last year. It's on Medium, okay? And we get at the kind of nature of process that it's the water we swim in. We tend not to see it. It's invisible to us because it's part of everyday life, even in manufacturing. And we kind of expound on what's going on there. And so I encourage you to read it. I'd love to hear your feedback. And if you're ever in Atlanta, please come visit. Happy to give you a tour of the campus or of the lab. And thank you for coming today. It's been really fun. And if there's any time left, I'd be happy to take questions.
When you say you harvest, what's that process?
Yeah. Yeah. So the question was about how do you harvest nanowires from the geodes, right? So harvesting right now is a sonication process and then a centrifugation process. So when you break open those capsules, you have big, if you do it right, you have big pieces of capsule. And you have little small nanowires by comparison. So you sonicate to break things, and then you centrifuge to move the big pieces down and keep the smaller pieces up top. So that's the basic idea. It's, I'm sure, not the only way to do this, but it's the way we've been pursuing it for a little while now.
Okay. Any questions from the virtual audience? I don't see. I have a question actually about the Geode as well. What's the sort of yield rate on getting those the nanowires that you're growing out in like a tractable manner?
Yeah, I mean that's kind of where we are now, right? So there's a lot to do that. Get all the chunks of shell away to stabilize the wires so that when you do that, they don't agglomerate.
Okay.
One of the things that's nice about the Geode shell from a processing perspective is that it's a substrate. You can imagine moving this powder from step to step to step in an industrial process one day, and the wires are anchored somewhere until you're ready to release them. So I think it's a huge benefit. But harvesting them is something that's going to need a lot of work. The other thing I'll say is that, you know, for the transistor work, you got to get them out. I don't really see a use of a bunch of transistors in a Geode. But we developed Geode originally for transistors, fully expecting to harvest everything. And as we've gone on, we have found a ton of different ways to use nanowires in microcapsules as is. So don't build the whole device, but the ability to encode, control the shape of nanowires, marry their properties to the properties of that silica shell. Turns out there's a lot of opportunities for other technologies, especially with the scalability that we can achieve with Geode. So we'll see.
Great, thank you. Any other questions from the audience? What about the virtual audience? Okay, so we have a question from virtual audience. When you remove PMMA on the silicon, it looks like it was etching isotropically. Do you get any undesired growth due to PMMA thickness difference, since the thickness of the inhibitor polymer affects the selectivity?
Yes. I don't think I know enough yet to tell you the answer to that specific question, but certainly, you know, residual polymer, if we're not careful about removing it from those lightly doped regions, will be an issue. We see pretty good resistance no matter the thickness, at least in the regime we're looking at, for the masks to block deposition. We really haven't seen an issue there. It's been, for us at least, more of an issue of making sure you remove all of the polymer from the lightly doped channel region.
Yeah.
That's been the main challenge.
Okay. And maybe on top of that, it does look pretty controlled, but do you find that it blends at all, or it sort of bleeds into the
that's
other areas that you don't
when I
intend?
first started showing these data, people who do self-assembled monolayers to block and control ALD.
Yeah.
The immediate first thing they said was, well, your polymer has a pretty decent thickness, so it could fall down, and even if you grow it here, the chains can fall over and maybe block some of the region you don't want to block. We haven't. That's not at the forefront of our problems right now, I guess is the way I would describe it. And I think the polymer is really nice because SAMs can be really delicate. So in a process like this, having a thick enough layer to act as a mask has proven to be helpful in multiple instances.
Okay.
The nanowire surface also is not a planar surface. It's right. A nanowire has cylindrical symmetry, and you can think about all the different crystal facets that you might expect around a nanowire.
Mhm.
So area selective ALD could behave very differently on some of those different facets.
Sure.
So something you design in really easily on a planar surface
Yep.
can become really hard when using SAMs on a nanowire. So having kind of a big, massive chunk of stuff to
Right.
block ALD so you can get it to happen all the way around all the facets of the nanowire,
Yeah.
we found to be advantageous.
Okay, great. Thank you, Kay, for your question. Anybody? Okay, good. He said thanks. Anybody else from the audience have a question? Okay, well, let's thank our speaker one last time.
Thank you.
For the great talk.
Thanks so much.